Hello friends, welcome to our sessions for understanding the sensitive ground faults. Furthermore, we discussed about the sensitive ground faults, about the types, and about the stages. We discussed about the general functionality and the functionality of each stage that we started from the stage of 3i0 greater by measuring of cosine of this phi or sine of this phi. And today we are on that in the first method. Here, this is the general block diagram, functionality block diagram. And furthermore, we discussed about many more basics of these blocks. But from today onwards, we will discuss blocks by blocks because we already understood some of the basics. The first block is the directional measuring method by cosine of phi and sine of phi, and another the phi correction or the correction angle for our proper system. Here we have a three-phase system, and suppose on the first phase some fault occurs, and these are the direction of the fault currents. If we ground this system with a arc suppression coil, which is called also Peterson coil grounded system, for better understanding and for simplicity, we simplify this circuit as like this. This is just a coil grounded and a fault occurs on the first system, and another part in during the fault. We know that before happening of the fault, each phase of our transmission line, our feeder, can have capacitance with the ground. These are the capacitances in the ground because it is distributed, but we draw it in a lamped circuit. This is distributed. This capacitance is distributed over of each one of the line with the ground, and this is grounded with Peterson coil. We know that this part here. This guy is the current of the capacitances and this capacitive current of the system, and this is the current which is feedback to the system through a coil, so it is inductive current. With the method of Peterson, we are trying to make our system impedances neutralize. It means anyhow we should try to make IL equal to IC of the system. So the important point remains is the current, the resistive current of the fault, because when IC equals to IL, then no current flows through the ground, almost, but few amount of current which try to flow, that is the resistive current, which decides the type of the fault, which decides the amount of the fault current to flow. So for the systems with suppression coil grounded, we need to have our system configuration or correction angle like this. Here in this system with the coil grounded or suppression coil grounded, here the most decisive part for our fault is the current, which is resistive. It means it should be in phase with the V0, the 3I0, which is decisive for the fault. That is the current which is in phase of the V0. So our directional measuring we select as a cos phi, cosine of phi of by measuring the angle. This is the angle of this 3I0 with respect to V0. And our correction angle is 0 because this one should be our symmetrical line. This should be our symmetrical axis. Because the part of the current which is perpendicular to the symmetrical axis, that part is decisive. That part is going to be used during the analysis of the system and for fault detection. So we select this axis, the symmetrical axis, that should be in 90 degree with V0, and it should be on the line of P, so it should not have any tilting angle. So the phi correction we set as a 0 for the coil grounded systems. And the method for the measuring, we select cos phi because we need this part of the current perpendicular to the symmetrical axis, which is decisive for the type of the fault which it should be used for the functionality of the relay. In the next session of our discussion, we will discuss if our system is resistive grounded or isolated system. And we will discuss that what should be the setting, what should be the direction measuring method, and what should be the phi correction.